Welcome to part 4 of Maxvi's Verilog tutorial series. In this video we will discuss about lexical conventions in Verilog. First we will see how white spaces and comments can be utilized effectively in Verilog. Next we will explore the various operators available in Verilog and understand their usage in hardware description. We will then discuss how numbers are represented and manipulated within Verilog, covering both integer and real constants. Following that, we will learn how to handle strings in Verilog with practical examples. Moving on, we'll examine how identifiers can be used in Verilog, focusing on naming conventions and best practices. Finally, we'll look at the reserved keywords in Verilog. White spaces are used in strings and can be incorporated using the double quotes. The table below shows the semantics of white spaces in string sequences. \n represents new line character, \t represents tab character, \ represents escape character. Followed by 3 digits represents octal character. A character specified in 3 octal digits if less than 3 characters are used. The following character shall not be an octal digit. Implementations may issue an error if the character represented is greater than 377. This example demonstrates the use of the new line escape sequence \n. The $display function outputs hello followed by a new line character and then world. This is useful for formatting output where you need to display text on separate lines. This example showcases the tab escape sequence \t. The $display function outputs hello followed by a tab character and then world. Tabs are often used to align text in a structured manner within the output. This example illustrates how to include a literal double quote within a string using the escape sequence \. The $display function outputs the phrase he said hello world. Escaping character ensures that special characters are interpreted correctly within strings. This example demonstrates the use of octal escape sequences. The $display function outputs ASCII character A, where 1021 represents the ASCII character code for A. Octal escape sequences are useful when you need to represent characters by their numeric ASCII values. Comments are used to increase the readability of code by providing explanations or notes within the code itself. They are ignored by the simulator, meaning they do not affect the execution or performance of your Verilog code. Verilog HDL offers two forms of comments. The first type is the single line comment. Single line comments start with double forward slashes. Any text that follows these slashes on the same line is considered a comment. The second type is multi-line comments. These comments start with /* and end with */. Any text between these markers is treated as a comment. This type is useful for longer explanations that span multiple lines. Using comments effectively can greatly enhance the readability and maintainability of your code. They are particularly useful for explaining the purpose of specific code blocks, leaving notes for other developers who may work on the code in the future, or temporarily disabling sections of code during debugging. Operators are crucial as they determine the type of operation that is to be performed in your code. Verilog HDL provides 3 kinds of operators, each serving a different purpose based on the number of operands they work with. These operators are unary operators, which work with a single operand, binary operators, which work with 2 operands, and ternary operators, which work with 3 operands. Unary operators operate on a single operand to perform actions like negation and logical or reduction operations. Binary operators, on the other hand, work with two operands and are used for arithmetic, logical, and bitwise operations. They include common arithmetic operations as well as bitwise and logical operations. Finally, the ternary operator provides a compact way to write an if-else statement with the syntax condition question mark true expression colon false expression. Depending on the condition, either the true expression or the false expression is evaluated. Let's explore an example of unary operators in Verilog. We have a module named unary underscore example. Inside this module, we define a 4-bit register named A and initialize it with the value 4 tick B1010. In the initial block, we use various unary operators and display their results using $display. First, we have the bitwise NOT operation. The code A inverts all the bits of A, so 1010 becomes 0101. Next, we use the logical NOT operator. A. This checks the logical state of A. Since A is non-zero, not a return 0, we also have reduction operators. The reduction and operator performs a bitwise and reduction across all bits of A. For 1010, the result is 0. The reduction or operator performs a bitwise or reduction across all bits of A. For 1010, the result is 1. Finally, the reduction XOR operator performs a bitwise XOR reduction across all bits of A. For 1010, the result is 0. These operations are displayed using the $display function. Next, let's look at binary operators with the binary underscore example module. In this module, we have two 4-bit registers named A and B. Initialized to A is 1010 and B is 0101 respectively. In the initial block, we perform various binary operations and display their results. For addition, a plus B gives us 15. Using binary addition, we get 1111. Subtraction, a minus B results in 5. Using binary subtraction, we get 0101. Multiplication of A and B results in 50. This result is 6 tick B110010. Division A by B results in 2. In binary, this is 0010. We also perform bitwise operations. The bitwise and operation A and B results in 000. The bitwise or operation A or B results in 1111. The bitwise XOR operation A XOR B also results in 1111. Logical operations include logical and A and B, which checks if both A and B are non-zero. Since both are non-zero, the result is 1. Logical Oregon or B checks if either A or B is non-zero. Since at least one is non-zero, the result is 1. These operations are displayed using the $display function. Finally, let's examine the ternary operator with the ternary underscore example module. In this module, we have two 4-bit registers named A and B. Initialized to A is 4 tick B1010 and B is 4 tick B010101 respectively. In the initial block, we use the ternary operator to compare A and B. The ternary operator syntax is condition question mark true expression colon false expression. Here the condition is a greater than B. If A is greater than B, the expression evaluates to true, otherwise it evaluates to false. Since A is greater than B, the condition is true and the result is true. This result is displayed using the $display function. Integer constants in Verilog are used to represent fixed point numbers. They can be specified in different bases: binary, octal, decimal, or hexadecimal. Look at the syntax of the integer constants. It represents size of the number, whether 4 bits, 8 or 16 bits, and etc. Base of the number represents whether it is decimal, binary, octal, or hexadecimal, along with the number. 4-tick B1111, which is a 4-bit binary number, equivalent to 15 in decimal. 6-tick O27, which is a 6-bit octal number 27, equivalent to 23 in decimal. 8-tick T12, which is a 8-bit decimal number 12. 4-tick H A, which is a 8-bit hexadecimal number A, equivalent to 10 in decimal. Integers has both signed and unsigned values. The x value, also known as don't care, represents an unknown or undefined value in Verilog, used in situations where the value of a bit is irrelevant or unknown. The Z value represents a high impedance state in Verilog, often used in tri-state logic, indicates that a signal is not being actively driven by any source. In Verilog, real constants serve a crucial role in simulating and modeling floating point numbers. Real constants are structured as integer dot fraction, where the integer part represents the whole number component and the fraction part captures the decimal precision. For instance, simple real number, consider 3.14. Here 3 is the integer part and 0.14 represents the fractional component, expressing the well-known approximation of pi. Negative real number, take minus 2.718, where minus 2 is the integer part and 0.718 signifies the fractional part, representing the mathematical constant e. It's important to note that while real constants are invaluable for simulations and test benches, they are not synthesizable. This means they cannot be used directly to generate hardware logic. In Verilog, strings are sequences of characters enclosed in double quotes. They are primarily used for displaying messages in test benches and simulations. Strings are stored in reg variables, and the width of the reg variable must be large enough to accommodate the string. In the truncation underscore example Verilog module, an 8-bit register named small underscore str is used to store a string. In the initial block, the string hello, which requires 40 bits, is assigned to small underscore str. Since small underscore str can only hold 8 bits, it truncates the string, storing only the last 8 bits. As a result, when using $display to print the content, only the final character O of the string is shown, leading to the output truncated string O. Strings in Verilog are primarily used for simulation purposes and are not synthesizable. Limitations are that string operations, such as concatenation, are more restricted compared to those in high-level programming languages. In Verilog, identifiers are names used to identify variables, modules, functions, and other entities in your code. Identifiers must begin with a letter or an underscore. They can be followed by letters, digits, or additional underscores. It's important to remember that identifiers are case sensitive, so signal and signal are considered different names. Additionally, identifiers cannot be Verilog keywords. These rules ensure that your identifiers are both unique and meaningful in Verilog code. In Verilog, some identifiers are valid while others are not. For example, valid identifiers are CLKLK, reset, data1, and road underscore n. These names follow the rules for identifiers. On the other hand, invalid identifiers include one data, hash signal, and data at home. These are invalid because they either start with a digit, contain special characters, or do not follow the proper naming rules. To be valid, an identifier must start with a letter or an underscore and can include letters, digits, or underscores, but not special characters or digits at the beginning. Keywords in Verilog are reserved words predefined by the language for specific purposes. These keywords cannot be used as identifiers. Some of the keywords include if, else, for, while, begin, end, case, and default. It's important to note that keywords are always written in all lowercase letters. Thank you for watching. If you have any questions, just leave a comment below. Have a great day.